Okay, so let's start our lecture today. So, uh, yeah. So last time I think we just showed this inequality. Uh, whenever this z is belongs to this chosen compact set, and then this argument holds for the all the tail factors. Okay, so yeah, so yeah, so let me continue. So give me 1 second. So I need to turn this internet on. Okay, so then he says that shoot. Okay, so uh, okay, so thus the Weierstrass M test M test reduces to the problem to the convergence of the sum of all the lattice point of modulus of omega cubed. Okay, so we have already showed the convergence of this guy in the very beginning. So here I just omit this fact. So I just stayed here and then without proving it. And then so let me just erase this one. Okay, so yeah, so he is explaining why this sum of omega to the negative third power converge. So therefore okay, so therefore okay, let me just use this space. Okay, therefore we have the sum of all the lattices of so here he's just using, okay, so let me just follow this notation here. So of the capital log of 1 minus z over omega plus z over omega plus z over omega squared. Sorry, plus z squared over 2 omega squared. Okay. and then this guy. Oh, I think I'm running out of ink. So convergence. Okay, still can be written. So convergence absolutely. And uniformity. Okay. Okay. So so definitely we know that the tau is summable, right? So given that this omega cube is actually summable for the tails, but for the heads, because for the heads the sum is always finite, right? Because we can just take the supremum for the yeah, I think this case needs to be taken avoiding the lattices. Otherwise, yeah, so this case needs to be taken avoiding the lattices. Wait, I don't think I need to avoid lattice because yeah, okay, my bad, because when this z is equal to one of the lattice point, right? So then the product will be 0. So the zeta function, the sigma function will just be equal to 0 when this z is equal to one of the lattice point. But here this z cannot be equal to 0, right? Sorry, for here this z cannot be equal to the lattice point because you will have log of 0, which is non-defined. So yeah, let me check more carefully. So yeah, so okay, so let's state this question for now. So question so if this complex set K intersect the lattice point, so I'll use the notion wedge take away 0 for the lattice point. It's not empty. Then shoot. I think I need to switch to another pen. So then we have yeah. So then we have then we have that log of 1 minus z over is not defined. On z equal to omega I, which is inside the intersection, right? Okay, so this might be a potential issue. But so the good thing is that so the good thing is that this issue only happens when this indexing is small, right? But because when the indexing is big, the omegas will go away up to like a radius 2r, right? And then we show that the convergence is okay for the tail part. So, but this happens only when only for finitely many head part, right? Head part where omega I is so where the modulus omega A is less than r, okay, where this r is like the radius that so where r is like the maximum radius that points in K can be, okay, so let's see. So okay, so for now, let's just assume that okay. Assume for now that this K is actually a subset of C minus the wedge point, okay. Because some technicality, because this wedge, it denotes all the lattice point including 0. So here, in order to think of the formally all the lattice point, I should take away the 0. So here, since I take away the origin, so I'm just gonna give it back, okay. And then I'll ask so maybe I'll ask the okay, so let's see what's going on for now. Okay, so will we encounter any issue? So okay, so so then it gives you the absolute, give us the absolute and uniform convergence on K, right, by the Weierstrass M test. Because for each of the modulus term, right? So for the tail terms, it is the upper bound is actually summable, and there is only finitely many head terms, and for the head terms we can just pick the upper bound to be the supremum of this function, because this function is holomorphic on K, so therefore yeah, so therefore we can take its maximum over the compact set K, right? So the maximum is actually the maximum of the modulus. Yeah, the maximum of the modulus on K. So and then the whole thing is actually summable. Yeah. So that satisfies the condition for the Weierstrass test, so that it gives the absolute and uniform convergence on K. Okay, so let me make sure that I get the right condition. Okay, yeah. Okay, so assume for now. Okay, yeah, assume for now. Okay, yeah, so there's no problem. So oh, okay. Okay, so he is treating this in another way. Okay, so we don't need to care about this one, because shoot. Okay, so for now let's just follow the ChatGPT. Okay, so let's just ignore this K for a while. Yeah, we can just say that. Okay. Okay, so I'll just erase this one, because he is using the K for the general compact set K. Okay, so then he's saying that this converges absolutely uniformly on K, but I don't think it is true, including the head part. So I'll just erase this one, but I think yeah. So let's just erase this one. Okay. So so what I'll do is that then he says some argument about only the tail part. Okay. So let's see. So so for the okay, so now, so for the okay, so here, since I stated the tail factors here, so let's just continue the argument about the tail factors. Okay, so yeah, so maybe I will just stay here. So for the tail factors, define so define capital L of NZ to be equal to sum from J start from N0 plus 1 to capital N. Okay, so he's using only the tail factors. So sum over the log of 1 minus Z over omega J plus Z over omega J plus Z squared over 2 omega J squared So then, yeah. So I think what he means is that for those points that such that the 1 minus z over omega is contained in this disk. Okay, I think this is what he means by the tail factor here. So the M test shows that this Ln converges oh shoot. Okay. This Ln converges uniformly. Yeah, so there's no problem. Because in this case, this z is only contained in k, and this omega j is away from a bigger radius, the radius 2r, right? So yeah, where the radius r is actually contains the set k, and when we have the radius 2r, the k is fully contained in the disk of radius r, center at origin, and then when this tail is large, this omega is being actually contained in the disk of it's actually away from the disk of radius 2r, so that it just avoids this k. So there's no issue of so there's no issue about like this undefined for log. Okay, so on k to a function let's say L. Okay. But we have the exponential of ln(z), which is equal to the product j from n0 plus 1, yeah, to n 1 minus. By the way, I think this is a little bit misleading right now, so maybe I think I should erase this one. Yeah, so we are not considering like showing that this Fn and Gn converges separately. Yeah, it can be give us more room. Yeah. Okay. So maybe I won't use this one right now. So z over omega j as exponential of z over omega j plus z squared over 2 omega j squared. So yeah, so let's see. So so he's defined the log first, and then he's doing the sum in the exponential way, so that yeah, okay, so that there's no issue about like log of a plus b, whether log of ab is equal to log a plus log b plus some 2 pi I issue. Yeah, so okay, so yeah, so when we take the exponentials, like all the 2 pi r are cancelled out with the exponentials, right? So let's see. So why this 2 pi I of ln z is equal to that? So yeah, because I think that is just the property of the exponential map, right? Because if you take, let's say, take 2 points, yeah, the product of the exponentials is equal to the power the sum of so sum of the powers of the exponentials is equal to just the product, right? And then e to the log of this guy is just the original thing. Okay. So this is the property of the log. Okay. So yeah, so this is true. So and then what happens? Let's see. Okay, so since we have Ln converges to L uniformly, so we have that e to the Ln converges to e to the L uniformly on K. Okay, uniformly on K. Okay, so I'll show this part next time. Okay, so okay.